All right, welcome back. I'm sorry this is a little bit late. I forgot some of my stuff at class, so I had to go back to pick it up. But I just wanted to reiterate kind of what I want you guys to do during these lectures and kind of the point of doing it. So what I'd like you guys to do during the lecture is make sure if you have a textbook, anything like that, open it up to the given section. It doesn't have to be our current textbook, but you can look at something for reference, have some place where you can take notes, refer back to it in class. So when we get to class and I start talking about the material, you have something that you've already written down so you're not furiously copying away while I'm talking. Because when you're copying things down, you're not really thinking. But that's the basic idea. So let's get started. We have our two main concepts that we introduced last time, the idea of resistance. So the resistance of a piece of material depends on its shape, what material it's made of, things like that. And then the resistivity, which is just a property of any given material. So iron has a certain resistivity, or copper, and it doesn't matter the shape. It's just a constant of that material. But as you heat up a material, the internal kinetic energy increases. So the atoms are moving around, and as that happens, they have I guess you can kind of call it a cluttered path. So what happens as the electrons try to travel down, instead of going in a straight line or a mostly straight line, they're bounced around back and forth. It's like going through a pinball machine. So they bump into each other, so they transfer energy back and forth. All right, so let's look at kind of two versions of the constants we have. So 20 degrees Celsius is kind of a reference point, and what we're going to have is a rho 0 and r 0 are the resistance, are the resistivity and resistance at 20 degrees Celsius. For the constants you look at in the book, or the ones I'm going to show in class, I put up in class on Wednesday, but I'll do it again on Monday. Those resistances and resistivities are usually referenced to 20 degrees Celsius. So as a function of temperature, it turns out they increase. And the amount they increase looks like this. So rho is rho 0 multiplied by 1 plus this constant alpha times the temperature that it's at minus 20 degrees. So as it's looking on there, it looks at how much you're above or below. If you're below 20 degrees, this factor gets negative, so it gets smaller and smaller and smaller. And then eventually it's going to get bigger and bigger with higher temperatures. And the same thing for resistance. The resistance of an object decreases. Now, as that goes along, you can kind of reference those two different points. Look at the way a problem involving temperature-dependent resistance or resistivity, it'll mention something about, at 100 degrees Celsius, the wire, the light bulb uses up this much power, but then when it's been on for a while and it's at 200 degrees Celsius, probably not going to be 200 degrees Celsius, but I'm just making up numbers off the top of my head, what is its new resistance? So you can manipulate the numbers around a little bit like that. Okay. Alpha, it doesn't really have a nice, succinct name. It's just the temperature coefficient of resistivity. All right, but to find alpha, basically we need R or rho at two different temperatures, either at the reference temperature or even two different temperatures. And basically you use those to find rho 0, R 0, or alpha. And it all depends on what you're given. And whenever you're using it, always make sure you're looking at the difference between the current temperature and 20 degrees Celsius. Here's an example of how resistivity is going to change for different materials. Just to make the numbers look nice, they use micro-ohm centimeters instead of ohm meters. But lead is fairly linear going across there. Iron is linear for most temperatures. Then you start getting down below room temperature, so 0 degrees Celsius is somewhere around here, then it starts becoming nonlinear towards 0. Aluminum, copper, they're all linear towards 0 there. But if you look at it, if you look at lead and you go its resistivity, before it gets to 0 degrees Celsius, it's at 0 resistivity. and that's when it becomes a superconductor. A superconductor is an object that is a perfect conductor. It has zero resistance. It reacts instantly to any magnetic fields, completely getting rid of them. Like, a normal conductor, the charges move around so that the electric field is zero inside. In a superconductor, they move themselves around in such a way that both the electric and the magnetic field are zero inside. So they're perfect reflectors. They're perfect repellers of magnetic force. So here you have, in a very cold material, you have a magnet that's floating above this superconductor. So the superconductivity, the amount of the place where an object becomes a superconductor is called the critical temperature. So if you're above that, you don't get it to be a superconductor, but below it you can. And you can change it. There's a whole, if you study, I can't remember the name of the area of study physics I studied, condensed matter physics. Condensed matter physics is basically everything except gases, liquids and solids and things like that, or even weird combinations like liquid crystals. But one of the main things you have to study is superconductors. There's a lot of interesting properties of it that I don't really want to get into at this point, but just to know they're out there. But most superconductors are very, very, they only become superconductors at very, very cold temperatures. And what so-called high TC superconductors are ones that are above 77 Kelvin. And the reason that's useful is that's the temperature of liquid nitrogen. And liquid nitrogen, while you don't usually get it in most places, is actually fairly cheap and easy to use. And here's kind of a show. You can see what some of the different materials that are superconductive. The blue ones are just normal superconductors. You just get them very cold and they'll start becoming superconducting. The green ones, you have to apply a high pressure because otherwise their properties change under a normal pressure. All right, so that'll be the end of this first lecture. So you can move on to the second one on something it's probably more familiar if you've taken high school physics before, the idea of electric power and how much it's used.